Good afternoon, Topology gang. I hope this video finds you healthy and doing well. I hope you guys are surviving the heavy load of distance learning. I've heard from many of you that this is way more work than usual, and I certainly can empathize with that. For me, it's been way more work as well. I'm barely keeping up, actually. But surviving, and summer is coming soon, so we're going to make it. We're not going to go too much farther as a class. We are going to get a little ways into chapter 3, though, and we're going to look specifically in this chapter at functions and then continuity and what that has to do with topology. And hopefully we're going to end with the idea of what's called a homeomorphism, and that will connect us to some of the interesting things that we saw when we took a day and just kind of played around and looked at how topology is being used in really cool ways. Somehow all that we're doing so far does seem so remote from what we saw in those videos. And if we can get to the idea of a homeomorphism, that will help bridge that gap just a little bit. So that's where we're going. Today's lecture, we're going to cover 2 sections. And a lot of it, at least the first part, should be familiar. We're going to focus on the pre-image of a function, which you might not have looked at as much. So that might be new, but functions themselves should be something you've seen before. Certainly you saw it in discrete and other situations as well. So let's get going. So let's take 2 sets, D and C. Let D and C be sets. So a function f from D to C is a pairing, or mapping if you prefer. It's a pairing of each element in D to a unique element in C. And it is important that we realize that if I have a 2 over here in D, let's say, I can't send 2 to 3 and to 5. Those are different elements. I can't do that and still be a function. So you really, it's important that we catch, right, that you're sending each element in D to a unique element in C. So you're very familiar with the name of D. We typically call D the domain of F. Not of C, of F. And we call C the codomain. You might think of the range, but we're going to call C the codomain. So for us, there's the domain and the codomain. I want to point out to you that D and C need not be distinct. They can be the same sets. In fact, all of Calc 1, we're studying functions from the reals to the reals. So it's certainly fine if they happen to be the same set. Some notation. So we'll often write f of A equals B. That means we're pairing A with B. And if you want to picture, here's D, here's A, here's C, here's B, and so you can think about, in your mind, you can think about F as like assigning, mapping A over to B, or just pairing A and B together. And then we're going to call, let's squeeze in here, we're going to call f of A equals B the image of little a. So f of A is the image of A. In general, the image of F, this is important, we'll talk about this more, but the image of F is the set of all f of x such that x is in the domain. And of course, this is a subset of C. So the image of a function is a subset of its codomain. All right, so let's do an example together. Just a somewhat quick example, nothing too fancy, but we're going to have a function from the reals to the reals. Let's have f is defined by sending x to x squared. This notation is telling you what f does. F takes x and it sends it to x squared. You're used to the notation f of x equals x squared. It's the same. That's fine. Of course, the domain is the codomain is the reals. The image of f, in this case, it would just be 0 to infinity, which is a proper subset of the reals. F of 1 is 1, f of minus 2 is 4, so on and so forth. So nothing particularly tricky here. We're going to use many of the same ideas that you're used to. We're just going to focus less on the analytics side and more on the structural side, more on the algebraic side, thinking about this in terms of sets and so on and so forth. So back in discrete, you learned function composition. We use it all the time in our calculus classes. So if I have a function f from a to b, and then another function g from b to c, we can form the composition function, which we write g compose f. That actually goes from a to c. And how is it defined? Pause the video, think about it for just a moment. It's defined by g compose f of little a is g of f of a. And so that's, again, something you're familiar with. This holds, by the way, for all a and a. There we go. All right, so let's stop this video here, and then we'll go on in the next one and keep going.